Yeah, my name is Mark. I'm going to be talking about congestion resilience, congestion control on Sui, and specifically, it's basically how are you going to have your transactions actually executed and not get dropped on the floor. I don't know if anybody has had problems with Solana or any other networks recently. I've heard that there might have been some problems. My goal for this talk is I'm going to be talking a lot about how the sort of the inner workings of the Sui protocol, which may not be relevant like day to day if you're a builder or a degen. But my goal is that you leave this talk with kind of an intuitive model of how Sui works internally that you can use to think about congestion and how this is going to work for you in practice. If you have any questions, please just interrupt at any time if anything is unclear, anything that you want to know. So I want to start off with just talking about how Sui scales in general. Our goal with Sui is we want to have a network where our gas fees are not increasing as network traffic goes up. No gas wars on Sui. We don't have a limit on block space. We can, the protocol can expand to any number of transactions that, as long as we have enough CPUs to execute them. But no matter what we do, there might be some state inside the network that's going to be hot. So an example would be any kind of DEX. There's going to be state for that object. Maybe somebody wants to do a swap. Maybe a lot of people want to do a swap. Only one of them gets to be first at the bit or at the swap to do it. And so at some point we are going to have a congestion problem, no matter how much the overall network can scale. So how does Sui get this kind of scalability? It's through our object model, which has a lot of benefits for programmability. It also is really the key to our scalability, though. And when you think about Sui transactions, I want you, instead of thinking about addresses that are updating balances, I want you to think about transformations on objects. So you can imagine this is a Sui transaction, and it takes some input objects, and it spits out output objects. That's all that a transaction on Sui does. And by modeling our data this way, this is how we get this kind of scalability. So you can see, if you think about the whole Sui network, you can imagine this huge graph of objects that are connected by transactions. So transactions, they read in objects, they spit out new objects. And if you look at this graph, what you can see very quickly is that you have groups of transactions that have nothing to do with each other. So it's clear that these two transactions, they don't depend on each other, they can be executed in parallel. They can be executed on different machines, in fact. This is how Sui is going to scale. We're going to eventually shard our validators without sharding the chain. Right? It's going to be one L1 sharded across many machines, so we can scale to any number of transactions that we need to in the future. It's a lot of work to get there, but the path is clear. Unfortunately, object graphs don't always look this pretty. You might end up with something like this, where you have this nice pretty thing here, and down here you have a DEX, where it's just a lot of transactions hitting one object. Now our scaling story sort of breaks down, because these are all dependent on each other. Each transaction comes in and it mutates the same piece of state. The next one comes in, mutates the same piece of state. And this is not something you can parallelize. It's fundamentally sequential. So in that situation, we can't fix this by adding more machines. At some point, the demand on the system might outstrip the ability of the system to execute transactions. That's what congestion is. That's when there's more demand than we can actually satisfy. So I'm going to talk about how we resolve that situation, but before I can really get into that, I need to explain a little bit about how shared objects are scheduled and executed on Sui. I'm going to keep this high level, but you're going to get kind of an idea of how the protocol works internally. You might be familiar with Sui's fast path, which is for transfers, things that only operate on owned objects. We're not going to be talking about that. We're going to be talking about shared object execution today. Shared object scheduling is fundamentally driven by consensus. So we have a consensus engine that all shared object transactions go through. So they go in and they come out in these blocks that we call commits. And so when a commit arrives, it has a bunch of transactions in it. And what we do is we pull those transactions out, and then we assign them place in line for the objects that they use. So here we have two objects. TX1 and TX2 are reading one of them, and TX3 reads the other. So this is all that the consensus side of things does. It just puts things in their place in line. They execute later. They execute on different threads. So if you have a lot of objects, you can parallelize it. More commits come in, and we just keep adding the transactions to their queue. And what you can start to see here is that this second commit had 3 transactions that all wanted to read the same object. And you can see these things are starting to back up here. But what I want you to notice is that the uncongested object, the one on the bottom here, it's not affected. This 3.1, TX 3.1 can read that object as soon as it comes in. It doesn't have to wait. The other objects have to wait because they're in this longer line. So that's like one of the most important things about Sui is that when we do have network congestion, it's going to affect the object. It's going to affect the hot object. Other applications are not going to be affected. So this is why we're not going to have gas wars, right? You're not going to have to compete with whatever crazy mint or DEX or whatever is going on chain. If you're not actually trying to use it, you're not going to compete with it. So what we're starting to see, let me go back one slide. Yeah. So we're starting to see a little bit of backlog build up here, but it can get much worse. There's really no limit to how fast transactions can come in through consensus. And when they start coming in really fast, you can get into this situation where we're sequencing them very, very fast, much faster than we can execute them. And so you can see here that the transactions arriving from commit 2, they don't even begin executing until 2 commits later, right? Because of all the commits that were in commit 1. And this is a fundamental problem, right? There's just not enough, CPUs aren't fast enough, they're not getting faster anymore. And so at some point there's gonna be so many transactions arriving, we can't execute them all as fast as we want to. And this also affects checkpoint latency. Why does checkpoint latency matter? If you're building a DApp, you're generally going to be using a full node or indexer sort of as the source of data for your app. And as checkpoints start to lag, it just means that the data that you have available to you is farther and farther out of date, with respect to what the validators actually know. We want checkpoint rate to keep up with the commit rate. We want, right now, commits come out once every second. That's going to get faster. And so we want checkpoints to come out once every second. We want them to be executable within a second. And if we let these congestion events pile up, that's going to interfere with that. What you're going to see is you'll have this checkpoint. It can be parallelized. It has transactions on multiple objects. The next one, it's totally serialized. Everything is hitting one object. And so you get this long checkpoint. It takes longer to execute. We don't want that. So the solution is basically we defer transactions from one commit to the next in order to keep checkpoints from lagging. But unfortunately, that doesn't help us at all with shared objects. Shared objects, if you're sequencing too many transactions, then as new transactions come in, they're going to have to wait as long as they need to wait. They just have to wait until everything that was scheduled before them finishes before they can be executed. And so what's the impact of this on you? If you're doing a trade, this means you would wait longer for your trade to actually settle. If you're playing a game, you're just in line. It just increases the latency, the end-to-end latency that you experience either as a user or a developer. We don't want this. So how do we solve it? How do we handle congestion? So before I go any further, I want to say this is a work in progress. We're currently building the system. It should be out on DevNet and testnet in the next few months, and mainnet as soon as possible thereafter. But this is a work in progress. So what do? We have more work to do than we can possibly do in the time we have to do it, so we have to make decisions. So our solution is we're gonna figure out what the important transactions are. And right now, that just means transactions that have higher gas price set on them. So we're going to put those first. And then we schedule as many as we can. We schedule the top end transactions. We say, this is how many we have time to execute right now. The rest of them are going to go into a queue. So we defer these, and we say, we'll get to these later. The next commit arrives. We read everything that was deferred from the previous commit. We combine it with these green transactions that arrived from the new commit, and then we sort again. So now we find out what's the new top n most important transactions. And this process repeats. So now we schedule the top 3, and then anything that still hasn't risen to the top gets deferred again. We're going to keep going. Commits come in, we sort, we schedule, we defer. And if things are in the queue for too long, they get canceled. So this basically ensures that you don't just sit there waiting forever. When they're canceled, what does that mean? That means they execute, but they exit with a failure code that just says you were trying to read a congested shared object. We are ideally going to include in that error message information about the price that you would have needed to pay in order to actually get executed, so that you can adjust, make a higher bid, get re-executed. But importantly, if you're familiar with how Sui's fastpath objects work, this allows us to unlock your gas object and any other owned objects that were involved in the transaction, so that you can try again. Any questions so far? Does this more or less make sense? Yes? Sorry? Right. Yes. What's important? Right now, it's purely an economic mechanism. So Sui transactions have a gas price, which is basically a multiplier on the amount that you pay for the transaction. And so if you set that higher, you pay more for your transaction to execute, but you are higher in the queue, in the order. Yeah. TBD, I think right now we're looking at 10 commits, which is about 10 seconds. We also will most likely, there's also going to be a limit on the overall length of the queue. So if you have paid so little that you don't even make it into the queue, you get canceled immediately. So we want things, even in the case where there is congestion and you're not quite hitting the clearing price, we want still a pretty low latency experience for you. So it'll be somewhere, I would guess, between 2 and 10 seconds. And this is something we're very interested in feedback on. And this is like a new thing that is going to launch later? Yeah. So none of this is live yet. We're implementing it right now. Yeah, but we're hoping by end of summer at the latest we'll have something out. Yeah. Is there any limits on the amount of gas you can pay for transactions? Nope. No, pay as much as you want. So I think the end goal, what we really want here is we want this to be like an economically efficient system where the only reason you're paying gas is because you want access to a scarce resource, and so do other people. And so ultimately you should be paying, what it's worth to you, not much more than that, ideally. And then either you clear the price, or if there's somebody else to whom it's worth more, then they bid higher, they get access, and you don't. Yep.
We do currently have a limit of 50 Sui per transaction. Is that before or after multiplying levels of Sui?
I didn't know that we had a limit on gas price. That's interesting. Yeah, I have no idea if it's before or after. I don't think that. I mean, I could imagine very valuable. If you imagine somebody, you could just run a lottery, right? First 10, not even a lottery, first 10 transactions get to claim, 1,000 Sui out of this shared object. And the bids for that, you might expect to go quite a bit higher than 50 Sui. So we may have to revisit that.
Mark, yeah. Really quickly, when people ask the question, do you mind restating the question so everybody can hear it?
Of course, yeah, I should do that, yeah. So the last question was, is there a limit on how much gas you can pay? And the one before that was, how long is the queue going to be, I think. Yeah, yes?
How to prevent the MEV bot to abuse this system?
How does this relate to MEV? I'm not sure I completely understand the question. Do you mind, can you have the microphone? That might make it easier.
Excuse me. How to prevent the MEV bot to abuse the system? For example, the MEV bot can send about 10 transactions with higher gas. Then your transaction will be canceled.
Okay, right. So one thing I want to stress here is that I'm using very small numbers of transactions here so that things can fit on a slide. But in reality, today we can probably, for things like swaps, we can probably handle hundreds of transactions per second on a single shared object, and we have a lot of plans to optimize that. So a congested shared object in the future is going to be one that's doing hundreds, if not thousands of transactions per second on that single object. So it's not going to be a case where a single person can come in and outbid you and you get canceled. There has to be really like a large volume of traffic, and you're bidding under all of it, right, before you're going to get canceled. That said, I think the general point still stands, like, are there going to be ways for people to manipulate this? I think the answer is yes, like people find out ways, and we're going to be, I'm going to stay away from the pricing discussions a little bit for this talk because we haven't really delved into that too much. We've had a lot of conversations internally, and every time we talk about it, it's such a complex issue that we can't really make a lot of forward progress on it. So we're trying to get something simple out, get feedback from you guys as quickly as possible, and then iterate on that. Okay, so in the slides up to this point, I've sort of treated every transaction as being equal. In reality, that's not how it really looks. You're going to have some transactions going to take much longer, especially on Sui with our programmable transactions, where you can have a very complex transaction next to something that's just a swap, just a single swap. So things are going to take different amounts of time. So how do we measure the execution time for the purpose of computing this congestion? We can't use milliseconds, we can't use CPU cycles because this has to be deterministic. Every validator has to agree. So gas is obviously the natural choice. And I've sort of already covered this, really. Everything is going to be based on gas. Right now, our prototype system is going to be using gas budget just because the implementation is much simpler. So we are going to have basically a maximum amount of gas budget that we're willing to allocate within a given commit. And so in the future, we want to use actual gas consumption. That's trickier because you don't know what that is until after the transaction executes. So it's much harder for us to implement, but we will get there eventually. But what this means for you is that setting a more accurate budget on your transaction is going to make it more likely for you to be executed. So you can imagine we're trying to fill up this amount of execution time, and we have these two transactions to pick from. One of them fits, one of them doesn't. Since the measure is budget, this transaction might fit in that block when it actually executes, but unless the submitter sets a reasonably low budget, we don't know that. So setting a lower budget, instead of just, I think a lot of people right now, they just set 10 Sui budget or something just because there's no reason not to. In the future, if you're interacting with shared objects, it's going to help us and help you if you set a more accurate budget, but don't think that you have to get it exact. Like if you get it 25, 50% margin, that's still going to let us build an efficient high utilization system. I want to talk briefly about multi-object scheduling, because as you know, in Sui, a transaction can read more than one object. So the diagrams earlier are very simplified. It's every transaction comes in, gets assigned to one object. In reality, you could be reading any number of objects. So in this situation, we have three objects. We start a counter for each of them at 0. As transactions come in, we assign them to read the object. We increase the counter for that transaction to indicate how much gas we have allocated to that object for execution time. So far, so good, nothing complicated. But now this object comes in that reads the first and the second object here. So what happens in this situation is both of these objects are going to have their counter increased to sort of the time at which this transaction ends. Because the next transaction that comes in, it can't read this second object until after this one is finished. Get another unrelated one down here. And so what this means is you can have this sort of dead time where, boy, it would have been nice if we could execute something in that space, but because of the way things came in, we couldn't do that. If things had gone differently, we would have been able to do this ordering instead, which is higher utilization for the system overall. But it may be the case that this transaction outbid the next transaction that came in which case it needs to go first. That's what it paid for. So this is just sort of a fact of life. Like if the if the bids come in this way, we have to schedule it this way instead of doing the higher utilization solution. Okay, and I'll talk briefly about, so before I go on, any questions about scheduling, congestion? Tim? Oh, microphone, yeah.
Quick question on the previous slide. In this situation where you have like multiple objects that you're scheduling, do you take the, do you take the price between like, there's a price per object, but then there's also a kind of combined pricing between the two?
So right now, sorting is just the gas price on the transaction. That's it.
Okay.
I could imagine, I think this is probably too complicated to be practical, but you could imagine in the future, transactions could bid for each object that they want. And so you could have a transaction that says, I really want access to this first object preferentially, but I'm not willing to bid for the second object. And that might allow us to do this more efficient scheduling, because we could see that this transaction might outbid the other one with respect to the second object, but not with respect to the first object. I don't know if, that'll depend on feedback really that we get. Like, I don't know if we would do something that complicated for a while. Yeah, can you send the mic over there?
You mentioned that maybe one transaction would have to be ordered first because they paid more for it. Like, do the validators have control over how they order things, or do they have to conform to like the rules defined here, which is like whoever pays more has to go first? Great question.
Yeah, so Sui is a little different because none of this is happening like in a mempool or anything like that. So this is after consensus. So the consensus commits arrive. Every validator sees the same commit, because that's why we call it consensus. And every validator has to follow the exact same scheduling algorithm. If they don't, they just fork. So they really have no choice unless they just want to leave the committee. So yeah, they basically all have to respect this algorithm. So,
so any like ordering stuff like MEV would have to happen before the commit is created?
Yeah, and so there is actually a SIP that was just published for some MEV related things where the submitters are, the designers of it are doing something pretty simple right now. This came in from the community, by the way. This is not a Mysten Labs thing. They're proposing this mechanism where you can submit a soft bundle, which is just a way to get a bunch of transactions submitted and guarantee that they're in the same commit. Because right now, if you submit 2 transactions at the same time, they'll probably be in the same commit, but they might not be. And so what they can do is, if they want to insert a back run or something like that, they set the same gas price, like the exact same gas price as the transaction they're trying to match with, submit it, get it in the same commit, and then they can kind of, since the gas price is the same, they have a pretty reasonable expectation that those transactions are going to be next to each other in the final order. Does that make sense?
Yeah, thank you.
Sure. Question over here. Yep.
Can we get this? Excellent.
Is the gas allocated to a cancelled transaction consumed?
Sorry, can you repeat?
Is the gas allocated to a cancelled transaction consumed, or is it going back?
Yeah, so for canceled transactions, they will pay like the minimum gas, basically, at least in the first iteration. So it would be, if you imagine writing a transaction where you call a function that just immediately aborts on its first instruction, you still pay a minimum gas for the transaction because you still have to update the versions of all your owned objects. And so that's what we would pay for a canceled transaction.
Okay, last question. Here
we
go,
are
brother.
running out of time. Good.
Are gas fees replaceable after commit, or are they fixed?
What do you mean by replace? Oh, can you modify them later?
The ordering seem to happen after the transactions have been committed to. So in principle, could I replace the gas to ensure that I get the first execution?
So if you don't get the first execution on your first attempt, you would have to submit a new transaction with a higher bid. So yeah, once they're, by the time they show up in consensus, they're already certified by the validators. You're already locked into, an exact transaction. So I don't think, if I understand your question correctly, the answer is no. You'd have to just make a new transaction.
Thanks.
Yeah.
Thank you.
I think we are out of time. I guess I'm easy to find, people tell me, so feel free to ask questions later.
What's your email?
Mark, M-A-R-K, at mystenlabs.com.
Okay,
All right.
phenomenal.
Thank you.
you.